In this video, we're going to be talking about the area of a surface of revolution. Let's define what that is first. If the graph of a continuous function is revolved about a line, the resulting surface is called a surface of revolution. Previously, we used integration to calculate the volume of a solid of revolution. In this section, we will use definite integrals to find the area of a surface of revolution. We can do this in a way that is very similar to how we derived arc length in the previous section. Consider the function f of x graphed below on the interval from a to b. We want to divide the interval into n equal subintervals of width delta x. Here we're using that n equals 4. When we rotate f of x about the x-axis, we get the image on the right. Each of the 4 three-dimensional shapes that make up the entire three-dimensional shape is called a frustum. The surface area of a frustum is given by a equals 2 pi r times L, where r is equal to the average of the radii, where r1 is the radius of the left end and r2 is the radius of the right end, and L is the length of the slant of the frustum. So what we're doing is we're taking this shape, rotating it about the x-axis, and if we do that, we get kind of this figure here, and then it's connected like that. And in this scenario, R1 is this value here, and then R2 is this value here. And so what we're doing is we are finding the surface area of each of these 4 frustums. For the frustum on the interval x sub I minus 1 to x sub I, we have that R1 is equal to f of x sub I minus 1, R2 is equal to f of x sub I, and L is equal to the length of the line segment connecting p sub I minus 1 and p sub I. And p sub I, these are just points that are on our curve. So those are corresponding to that. And we know from the previous section that the length is equal to the square root of 1 plus the square of the derivative at x sub I star times delta x, where x sub I star is some x value in that subinterval. We're going to assume that delta x is small, and since f of x is continuous, we can assume then that f of x sub I minus 1 is approximately equal to f of x sub I star, and same goes for f of x sub I. We'll say that that's approximately equal to f of x sub I star. So the surface area of the ith frustum on the subinterval x sub I minus 1 to x sub I is approximately a sub I is equal to 2 pi times the average of the 2 radii times the length of the line segment. And because we are saying that these are approximately equal to f of x sub I star, we can make that substitution here, and then the 2 f of x sub I star divided by 2, those 2's would divide out, and we'd be left with this. And then we can replace this with basically the formula that we saw in the previous section in arc length. This means that the surface area of the entire solid is then approximately equal to the sum of the expression that we just saw from I equals 1 to n. We can get the exact surface area by taking the limit as n goes to infinity, and when that happens, it changes into a definite integral. If we wanted to derive a similar formula for rotating x equals h of y on the closed interval from c to d about the y-axis, it would work very similarly, and we would get the following surface area formula. These are not the standard formulas. Note that the square roots in both formulas are the values we defined to be ds in the previous section. So we will replace f of x with y and h of y with x. Doing so gives us the following formulas. So this is the surface area formula we would use if we're rotating about the x-axis, and then this is the surface area formula we would use if we were rotating about the y-axis. Now note, they're very similar formulas, and if we're rotating about the x-axis, then the opposite variable goes here. If we're rotating about the y-axis, then the opposite variable goes here. And notice that these 2 pi y and 2 pi x kind of look like the circumference of a circle, and that's not a coincidence. And then ds we can define to be one of these 2 boxed formulas, depending on whether we are integrating with respect to x or integrating with respect to y. Let's go ahead and put these formulas to use. Example 1 says set up but do not evaluate an integral for the surface area of the object obtained by rotating y equals 7x plus 2 about the x-axis, where we're bounded between y equals -5 and y equals 0. And part A wants us to do that with respect to x, and in other words, we are integrating with the differential dx. Since we are integrating and we're rotating about the x-axis, that means that we're going to be using this top formula here. And because we're integrating with respect to x, we're going to define ds to be used the boxed formula on the left. So for part A, our surface area is equal to the integral, and right now our limits of integration, we need to solve for new limits because our current limits are given with respect to y. So let's go ahead and solve for new limits. I have that my original lower limit is y equals -5. So I'm going to take my curve here and I'm going to sub in -5 for y. If I subtract 2 on both sides, I get -7 is equal to 7x. And then from here, if I divide both sides by 7, we get x equals -1. So that is our new lower limit of integration. And then for y equals 0, which was our original upper limit of integration, if I have 0 equals 7x plus 2, and if I solve for x, I'll get x equals -2 over 7. So my new lower limit of integration is x equals -1, and my new upper limit of integration is x equals -2/7. Now, I'm going to have my integrand be 2 pi times y, but because we're integrating with respect to x, I don't want to put y, and instead I'll put 7x plus 2. And then we have the square root of 1 plus. Here I'll go ahead and solve for dy dx, which is going to equal 7. So I have 1 plus 7 squared, and then dx. Let's go ahead and do some simplification with that. So s is equal to 1 plus 7 squared is equal to 50, and I can simplify the square root of 50 and turn that into 5 root 2. And if I multiply that with the 2 pi, that's going to be 10 root 2 pi, and I'll factor that outside of my integral. And then inside we have 7x plus 2 and then dx. So this is our answer for part A. Let's go ahead and move on to part B, where it wants us to integrate with respect to y. We're still rotating about the x-axis, so I'm still going to use the top formula, but now we're integrating with respect to y, so we want to use this definition for ds. So we'll have that the surface area is equal to, now we can use these limits of integration since we're integrating with respect to y, and then we have 2 pi, and again, because we're integrating with respect to y, I can just leave this as the y variable, and then we're going to go ahead and do 1 plus, and here we're wanting to solve for dx dy. You could use implicit differentiation. You could also solve for x in this case. If you did that, you'd get y minus 2 is equal to 7x. If I divided both sides by 7, we'd get x equals 1/7 times y minus 2. And then from here, you could get dx dy is equal to 1/7. And so we're going to go ahead and square that. Okay, so if I simplify the radicand, we get 1 plus 1 over 49. That's going to change into 50 over 49. And if I take the square root of that, we could rewrite that as 5 root 2 over 7. So I'm going to factor out 2 pi and multiply that with this constant that we just found. So that's going to be 10 root 2 pi over 7 times the integral from -5 to 0 of y dy. And it just asks us to set up the integrals and not evaluate them. So this is our final answer for part B. Example 2 says set up but do not evaluate an integral for the surface area of the object obtained by rotating y equals e to the x about the x-axis, where y is between 1 and 8. And part A, it says with respect to x, so let's go ahead and set up our integral. We're going to, again, need to solve for new limits of integration, because right now our limits are in terms of y. So for y equals 1, I'm going to go ahead and set e to the x equal to 1. If I take the natural log of both sides, we get x is equal to the natural log of 1, which is equal to 0. And then for y equals 8, we get e to the x is equal to 8. And then from here, if we take the natural log of both sides, we get x is equal to the natural log of 8. So our integral is going to range from 0 to the natural log of 8. And because we're rotating about the x-axis, we have 2 pi y, but we're integrating with respect to x, so instead of y, I'm going to sub in e to the x. And then we have the square root of 1 plus dy dx quantity squared. And if I come over here, dy dx is equal to e to the x. If I square that, then I get e to the x quantity squared, which is equivalent to e to the 2x, because I multiply the exponents there. And then we have dx. And that is the final answer for part A. Part B wants us to integrate with respect to y. So we have s is equal to the integral from 1 to 8 of 2 pi times y, which we could just leave it as y in this scenario, times the square root of 1 plus. And here, if I took the reciprocal, I would get dx dy is equal to 1 over e to the x, and notice that e to the x is equal to y, so getting a little messy here. So that could also be rewritten as dx over dy is equal to 1 over y. So I'm going to come over here and put 1 over y quantity squared, and then dy. And here is our answer for part B. And if you want, you could simplify this, and you could rewrite this as 1 over y squared as well. And that's our answer for part B. Example 3 says set up but do not evaluate an integral for the surface area of the object obtained by rotating y equals e to the x about the y-axis, where y is bounded between 1 and 8. And here in part A, we're integrating with respect to x, and then in part B, we're integrating with respect to y. Now, this is almost exactly the same as the previous example, but now we're we're rotating about the y-axis. So for part A, we have that the surface area is equal to, we're going to have the same limits of integration as part A in the previous example, and then 2 pi, and then because we're rotating about the y-axis, we put the opposite variable here, which is x, and we're integrating with respect to x, so we could just leave it like that. Then we have 1 plus e to the 2x dx. And then for part B, we have s equals the integral from 1 to 8 of 2 pi, and then we can solve this for x. If I take the natural log of both sides, we get, and the natural log of e to the x is just x. So instead of putting x here, I'm going to put the natural log of y, because we're going to end up integrating with respect to y. And then I have 1 plus, and from here, we can solve for dx dy, which we already did, but we know that the natural log of y has the derivative 1 over y. So if I square that, just like last time, that will give me 1 over y squared. So here are our answers for part A and B in this example 3. Example 4 says find the area of the surface formed by revolving the graph of f of x equals x cubed on the interval from 0 to 1 about the x-axis. So this is the first example that we're looking at where it actually wants us to integrate and find the area. So let's go ahead and do that. I'm going to go ahead and set up my integral. We have s is equal to the integral from 0 to 1. We are rotating about the x-axis, so I'm going to put 2 pi y, but we're going to be integrating with respect to x. So instead of y, I'm going to replace it with x cubed. So I'll put x cubed here, and then if I solve for dy dx, that's going to end up equaling 3x squared, and if I square that, that's going to give me 9x to the 4th power. So we have 1 plus 9x to the 4th power. Now, we need to actually solve this integral now. How are we going to do that? Let's use u substitution. I'm going to let u equal 1 plus 9x to the 4th power. Then du will equal 36x cubed dx. I'm going to divide both sides by 36. And so now we get s is equal to, we can factor out 2 pi outside of the integral, and I'm also going to factor out the 1 over 36. Because we're integrating with respect to u now, I'm going to write my new limits of integration as u1 and u2. And then we're going to get the square root of u times du. I'm going to rewrite this as u to the 1/2 power so that it's easier for me to use the power rule on this. So 2 pi over 36 will reduce to pi over 18. And if I take the antiderivative of u to the 1/2 power, that's going to be 2/3 u to the 3/2 power, evaluated from u1 to u2. I'm going to divide that. That's going to give me 1. That's going to give me 9. And then this will equal pi over 27. And then let's plug u back in. I'm going to have 1 plus 9x to the 4th power. And then that's all raised to the 3/2 power. And we're evaluating this between x equals 0 and x equals 1. So now we're going to actually plug in our limit of integration. We have pi over 27 times 1 to the 4th power is 1, times 9 is 9, plus 1 is 10. So I'll have 10 to the 3/2 power minus, and if I plug in 0 for x now, that's just going to simplify to 1 to the 3/2 power, which is just 1. So here is our final answer. That number there represents the surface area of the surface that's formed by revolving the graph of f of x equals x cubed about the x-axis. Example 5 says set up but do not evaluate an integral for the surface area of the object obtained by rotating the graph of f of x equals cosine squared x on the interval from 0 to pi over 2 about the x-axis. So we have s equals the integral from 0 to pi over 2. And then we have 2 pi. Because we were rotating about the x-axis, we'd put the opposite variable y, but we are integrating with respect to x, so instead of y, I'm going to sub that in for cosine squared x. And then we have the square root of 1 plus. So right now we have y equals cosine squared x. I'm going to take the derivative of that. So dy dx is equal to 2 times cosine of x. And then I need to use chain rule and multiply by the derivative of cosine, which is negative sine of x. And if I simplify that, that's going to be negative 2 sine x times cosine x. And I can use the double angle identity for sine to rewrite that as negative sine of 2x. And at this stage, if I wanted to square that, then that would give me sine squared 2x. The negative would go away since we're squaring it. So coming back up here, we have sine squared 2x and then dx. And that is our answer for example 5. And that completes this video on surface area.